energy, temperature, flow monitoring, and ultrasonic flow meters. And today, we are going to talk about a few topics. First off, how much water do you use? This is becoming a critical situation, not how much it costs, but whether you have access to any. Major issue, especially out in the western portion of the United States. Why do we need to monitor energy? Again, it's got everything to do with economics and your next door neighbor sharing the resources we all have. We're going to talk about the ultrasonic technology and how it works. How do you monitor energy? The tools of the trade, how you install equipment, the technology of such equipment, and of course, best practices in selecting types of metering and temperature equipment for your particular application. And as always, it comes down to cost. It's always, always, always all about the economics. So let's get started. Mankind basically started in caves. And we did that to get out of the element. And we got out of the element and we kept warm. And then after we went through caves, we went and moved over to buildings, houses, campers, fancy hotels, what have you, to stay out of the environment, to keep warm and cozy, to keep cool when it's hot, and when it's hot outside, when it's cold outside, to keep warm. And all those places end up to being a configuration I call a bubble. So we all live inside a bubble. It's the environmental protection bubble for the inside versus the outside. And while we're inside this bubble, things happen outside, as we said. That's why we came in the bubble to begin with. So first off, while we live inside this bubble, we need to have some access to the outside world, namely water. So we have an influent to the bubble, so we can wash and eat and take care of business. And when we're done taking care of business, we have some effluent from the bubble. So we have a gazinta and we have a gazauda into the bubble. But on a warm, summer day, especially like today, it gets very hot outside the bubble. And then the environment is affected inside the bubble, and we have to do different things to change the environment to the way we like it. So summer is great, but guess what? There's the other side of the coin, is winter. So we have hot weather, humid weather, cold weather, and so we need to make adjustments accordingly to contain our lifestyle and our environment inside the bubble. Now inside the bubble, to make it work, we have that influent flow and that effluent flow coming into a hydronic system, a bunch of plumbing, very similar to the arteries in your body. In this case there, we're going to use it to run our facility. So we have the gazinta flow coming through the hydronic system inside our bubble and effluent flow. And the reason, of course, we need that, as we said before, we need to get a drink, we need to wash our hands, we're preparing a meal, we're manufacturing a process, we're using it for chilled water, and so on. So we've got to have the water inside our facility. And once we use the water, we got to get rid of the water, so we have effluent and waste from our facility. As we said, we need to have a heating system and a cooling system inside our facility to control the environment inside our bubble. So we're all happy. So now that we've got that established, we all live inside a bubble, and we have the tools to manage the environment inside the bubble. The problem is the efficiencies of the bubble. So the first red flag that comes up is the cost of maintaining the bubble. The most popular phone call we get lately, we'll get calls from the CFO of a hospital, and they'll say, my goodness, my utility expenses are extravagant. My air conditioning and heating bills are out of sight. We need you to talk to our facility people to monitor our facility to give us a better running situation so we can economize in the operation of this building. So in this case there, it comes to heart that we need to monitor expenses so the people down top are talking to the people that run the plants inside the bubble to find better ways to run this operation from an efficiency and an economical situation. The other side of that coin is the resources. There are places out west right now that have minimized use of influent flow inside their bubble. They have water restrictions. There's droughts. They don't have the water, so you can't even put a price on the water. So it's an issue here. So we have limited resources, and as we move forward here, we may have additional limited resources. So we need to monitor it for both economy, to keep everything in overall operation, and at the same time, we need to monitor it because we have limited resources, and we'd like to be in the planet a little while longer. So as long as we can be here, that's off. So inside this hydronic loop that we have, I said before, the Gazinta and the Gazauta. And on the Gazinta side, we have the traditional city water meter. Go outside your house, go outside your building. Somebody's sending you water, and doggone it, somebody's going to send you a bill. And therefore, there's always a meter at the front door of the facility. So to economize and operate the energy management of your facility from a big picture, we need to take a look at individual metering points to get a better handle or mapping of what's happening. So we know there's a meter at the front door, and then sometimes there's even a meter at the back door. The effluent is a unique application. It's usually gravity-fed, partially filled, and it varies different in pipe sizes from residential to commercial. And the metering is a little more exotic doing something like that, but it's available. Some municipalities bill whatever comes in the front door, you get billed what's going out the back door. So if you have a manufacturing process, something that reuses the water, then your effluent is less than your influent. And so you might be able to economize if you had metering for that particular application. Perhaps you need to have monitoring for your chilled water applications. The east wing is hot, but the west wing is cold, so you might need to have one in the east wing, and you might want to have one in the west wing. Same thing goes with the heat, different variations and different zones inside the facility there. So when you need to economize, step one is where are the resources going to? Where are the zones? Maybe you have individual billing stations there. We need to break it down to individual metering points. So it all comes down to our natural resources, and it comes down to water. Water covers about 70% of the Earth and is vital for all forms of life. And about 96% of the planet's water is probably found in the ocean. The rest is in groundwater, glaciers, ice caps. And is a key ingredient to life on our little old planet. So throughout evolution of mankind, man has tried to figure out a way to harness the power of water. And of course, now he's learned how to harness the power of water. He needs the tools to control and to monitor it. So this is the reason that we're in business here. We have the tools to monitor and control this resource. So the source, step one, where does it come from? Well, we see desalinization there, but that's just a minimal part. So for the most part, everything is coming from groundwater, so it's coming from irrigation, water wells, maybe rain collection, reservoirs, but then the final effluent of that, in many cases there, you're not going to get a raw well water. In many cases, you'll get a treated water. So you go through a water treatment plant. And so you'll have meeting throughout all those different sources there. Then the clientele after that ranges all over the place. Of course, your residential at your house, your drinking, cleaning, waste, irrigation, and heating, and so on. The commercial will probably make up the larger portion of our audience there, where they're doing the drinking, cleaning, waste, irrigation, cooling, heating, processing. And then we move over to processing. We're in the manufacturing side here. So in the manufacturing, we can be making product, heating, batching, blending. The list goes on and on and on and on. You can be in the beverage industry. Orange juice, you don't get 100% orange juice. You get orange juice and water. So all these things are mixed together. And then, of course, after everything is processed and you're done with the water, you're done with the product, the final effluent is a water treatment, a wastewater treatment plant. So this case there, in theory, it's supposed to be a circle. The water comes in, you use it, it gets dirty, then it comes to the wastewater treatment plant, it gets cleaned, it gets dumped right back into the river, and hopefully comes in the circle there. But there's a lot of waste, there's a lot of leakage between the middle there, so it's not a complete circle of efficiencies there. So those are the things we need to take a look for. Those are the front doors we start. So we know where the problem areas are. So now we need to have those metering tools we talked about. Metering tools to monitor liquid flow and energy. So to do this, to make it practical and probable, we need to have technology that's easy to use. So you don't need to go away to school for a week to use the technology. So it would be delightful if this technology did not disrupt your existing process or your existing application. It also needs to be budget sensitive. Capital investment is fine, but if you buy, for example, a portable transit meter, they start at about $6 grand and go up. There's also the ability to get it. Now you don't have to make a capital investment. You can rent something by the week. So anybody can get a hold of the access, and it's easy to use, and it's readily available. So the technology that I'm talking about is a clamp-on technology. And in order to do energy, we need to do flow, we need to do temperature. In this case there, we start off with flow. This is called an ultrasonic transit time flow meter. And an ultrasonic transit time flow meter is clamped on the outside of the pipe, and it measures flow by using ultrasonics. In this case there, this picture in the middle here, I have a diagram that says the flow is going from left to right. And I take a sound burst from this transducer, shoot it across the pipe, ricochet off the back wall, come downstream to this sensor here, and I measure how long it took to get from the first sensor to the second sensor. Now remember, the flow is going left to right. I'm going to take this transducer and send a sound burst across the pipe to this sensor, but I'm going against the current. So it takes a longer period of time to transit from one transducer to the next. The differential between the transit time is what we use to derive how fast the volumetric flow is flowing through that pipe. The faster the flow rate, the faster the sound beam gets carried downstream, and the longer it takes to come up against that current. So the differential is what we use to measure flow, and we do it most accurately. So transit time, do not confuse it with ultrasonic Doppler. Ultrasonic Doppler sends a sound beam in and it bounces off suspended particles. If you don't have any suspended particles, an ultrasonic Doppler flow meter will not work. So for the most part, you will not see Doppler flow meters in the HVAC, in the water, the irrigation side of the coin, because it's too clean for the technology to work. The picture you see before you in the center there, this is called the V configuration. We traditionally use this in applications in 1/2 to 24-inch pipe sizes. Picture on the right, the same thing, but this is for larger pipes traditionally. This is called the Z, or the single path configuration. We traditionally use this in pipe sizes 24 inches or larger, or smaller pipe sizes that have pipe buildup, 50-year-old pipes, a little bit short runs of pipe. And the second thing, using ultrasonic flow meters, some people just think it's magic and works every place, has a limited specification just like every other flow meter technology. So in this case there, it needs straight run of pipe. Okay, everybody needs straight run of pipe. Everybody's flow meter needs straight run of pipe. In this case there, we need to have the traditional 15 pipe diameters for flow rates between 7 and 10 feet per second. If you were to size a pipe and put a pump in there, you traditionally size it up for around 7 feet per second. So that's what the 15 pipe diameters are. And you have a picture that looks like this symmetrical flow profile. Fastest in the center, slowest near the pipe wall. These different elliptical shapes are called Reynolds numbers, which don't have effect on the performance. What we want is a center line here, top half of the flow equals the bottom half of flow. We have a symmetrical flow profile. You will get your optimum performance with your ultrasonic flow meter if you have your straight run of pipe. With a short straight application, we call that an asymmetrical flow profile. And for example, I'm coming up this elbow here. This turn in this elbow, this is a shorter distance and this is a longer distance. You're going to get a tumbling effect at this point here. If you were to put your ultrasonic transit time flow meter here, you'd probably get a fault condition, and you probably wouldn't get anything at all. You need to go downstream, 10 pipe diameters, and put your sensor there, and another 5 on the other side. So when you have this situation, you are optimum performance with your ultrasonic transit time flow meter. Now, it comes in many different shapes and configurations. There's a variety of portable devices out there. There's a variety of dedicated devices, and there are some limits. We'll go over those in a minute or two there. But here are some of the more popular brands. One on the right is the Fuji Portaflow, and one on the left is a GE PTA78, and underneath here is a Dynasonics DXN hybrid. And over here, here's a non-contact meter dedicated energy meter. So the value of using a transit time flow meter, no holes in the pipe. So you don't have to shut down the process to put in your paddle wheel. You just clamp it on the outside of the pipe and the insulation, remove the insulation, put it on the pipe, and cover back up if you like. You can get them readily available online or through different manufacturers. You can buy them and you can rent them. So you don't want to pop for $6 grand for a meter, you rent it for $6.99 a week. So there's no more a limited access for funding to get portable technology. And the dedicated meters start at about $2 grand and go up depending upon the communication features. So there's no reason to not have dedicated primary metering points for this type of technology. And as I said, a transit time technology works on all applications that have a full pipe condition, traditionally pressurized, not required. Line size is 1/2 inches and up. They work on ultra pure liquids, so you can work on your DI water, demineralized water. You can work on the jet fuel, gasoline, various chemicals. You can work on water, well water, chill water, hot water. You can work on sewage, and you can work up to about 2% suspended solids. So it doesn't work on oatmeal, and it doesn't work on sludge. That's where you put your ultrasonic Doppler flow meter. So give us a full pipe, and away you go. And the technology's evolved to that it's a commodity item. And being that in days of yore, you had to call somebody out and they would come and make a field demonstration. Not the case anymore. If you have a 6-inch pipe carbon steel, you need model XYZ. That's it. It's that simple. It's just a water meter, and depending upon your needs, it has a variety of different features now. Some cases flow, some cases energy. Let's jump into some of the problem areas that we have in doing flow surveying for energy management. So we're back at the front door now. We're going to monitor the water usage coming into your facility. So that's the first thing we need to manage. And with that in mind there, everybody says, I hate that city water meter. It's always wrong. It's always reading high. Well, what we normally get is an inquiry. They'll have a city water meter outside. We'll go inside the building and we'll go in the basement, and they want a reference meter here. And lo and behold, our reference meter sometimes reads higher than the city water meter. And they'll say, my meter's wrong. No, my meter's right. A city water meter is a mechanical meter, and the older it gets, the slower it gets. So the worst thing you can do after complaining about your city water meter, say, city, please replace my water meter. I guarantee you your water meter bill will go up. So leave the old meters in place. It'll be in your favor. It's usually rarely in the city's favor. If it is, it's a mathematical problem with their computer. But if you were to read the display, old mechanical meters don't get faster. They get lower. So in that case there, keep that in mind. Now we move up to a larger facility, and we have a larger reference meter. And again, they don't like what the city water meter reads. And we get inside the building, and we now come down to limits of knowledge on how flow meters work. So here's a case. We walked into a hotel, perhaps, and we had an 8-inch city water line coming in, and they didn't believe the city water meter. They wanted us to evaluate it. So we come in the line. We put a flow meter on the pipe, ultrasonic transit time flow meter. And the maintenance personnel said, okay, we're going to turn some water on. Watch your meter. We'll be back in a minute. And they come back in a minute, and we notice our flow meter doesn't blink a bit. They said, well, did you see that? We said, see what? They said, well, we flushed the toilet a couple of times on the 3rd floor. Did you see it? And the answer is no. It's a matter of relevance and a matter of flow rates. Did you know that a flush of water with a old-fashioned toilet is about 1.5 gallons. New stuff, less than that. So 1.5 gallons and an 8-inch carbon steel pipe equals 0.0767 feet per second. I am not aware of any ultrasonic meter For that matter, any magnetic flow meter, any turbine flow meter, it can read that low. So you're going to miss toilet flushes on a large line size like that. The flow rate gets higher, you're doing good. Excuse me. So in that case there, if you're going to monitor this, you need to have the right equipment. Now, how can the city monitor this thing? Go outside and take a look at the meter. I think you'll find in many cases there, the meter is a compound water meter. A compound water meter is a meter that has two flow meters in it. It has a big 8-inch meter, and it has an itty-bitty meter, depending on the pipe size, 1/2 to 1 inch. And guess what? The smaller the line size, the higher the velocity. That's how they're picking up the toilet flushes. So it's two different flow meters there because the line size reduced, and that takes care of that problem. So this is a faux pas to get into. You can misflow, and you can mismatch the city water meter on a large line size if you have very low flow rates. Another mismatch that's commonly happening in energy management is assumptions. Everybody thinks the square footage for one building to another will have the exact same energy cost. So in this case there, main building A manufactured the chilled water and basically transferred it to building B and building C, and they return it back. So the energy costs, when were monitored, and we noticed that Annex Building B had lower energy costs than Annex Building C. And we couldn't figure this out. They were both the same square footage, the same personnel, the same operation. Everything was the same. So we went out and did a study. Building B, we found out, transferred its chilled water subterranean from Building B to Building A, under the ground. And this was in a warm climate environment. Building C transferred its chilled water on a raised catwalk outside in the warm Florida sun. So it was exposed more to the external environment, and had an effect on the overall energy cost. Every little thing plays a role. As we get deeper into this, you can find out that every little bit differences can make a dynamic effect on the energy monitoring of your application. Step one, you need to have a flow meter that's accurate. If you don't have an accurate flow meter, you have inaccurate data. So my recommendation when you're using an ultrasonic flow meter is to get something that's 1% of rate, and some of the meters we put on the screen there will meet that requirement there. Well, there's a lot of meters out there that cost far less that will not meet that requirement. So you need an accurate flow meter of rate. Some of the insertion paddle wheel flow meters of yore that have been around for a long time, industry standard, have accuracies of full scale. You can be a couple % off very easily just by using a brand new calibrated full scale paddle wheel flow meter versus an of rate meter. It's not doing anything wrong. People don't understand the differences between the two. Secondly, temperature. We are monitoring differential temperature between the supply and the return. And it can be very small, in some cases less than 10 degrees Fahrenheit. So, for example, if one sensor reads 1 degree high, while the other reads 1 degree low, the energy calculation could be 20% off. So, a self-contained, or at least a self-calibrated system with matched sensors is a requirement to have any intelligent BTU calculations. You cannot buy this inexpensive flow meter. You cannot then go over to one catalog house and buy bargain basement temperature sensor thermistor. You cannot go to the next one and go buy a second temperature sensor with another bargain basement catalog house, and I have a thermocouple. Put those two together and expect to get any intelligent BTU calculations. You got to have high-end temperature equipment. You got to have high-end flow metering to get the math. You want good math, that's where the investment needs to be made. So a traditional energy loop, what is it? Well, a hydronic system is basically a closed loop, and we're going to generate either heat or cold or hot or cold from the load, and it's going to be transferred through this loop to a boiler or chiller. So look at this. It is a closed circuit. So first off, if you want to monitor flow in such a system, you only need to monitor the flow on the supply side, or the return side if you prefer, because the Gazinta equals the Gazouta. So we can monitor flow on the supply. And then if we wanted to add energy to the recipe, we would add temperature. We would add temperature to the supply and temperature to the return. Now, the first thing you need to get away from is the actual temperature of the liquid. These are clamp-on high-precision RTDs. When they're matched pairs, they're calibrated better than 1% and much better than 1%. And in this case there, they will be a few degrees different from the process temperature inside the pipe. But that's not part of the equation. The equation is flow and differential temperature. So we don't really care what the actual flow or temperature is. We actually care what the differential is between the supply and the return. So if you get over that fact, this will be a very accurate system, and you can get the kind of numbers that you're hoping to get with a clamp-on ultrasonic flow meter system. So with a portable device or a dedicated device, you can clamp on, collect your information for an energy study, balance the loop, and move forward. Here's an illustration of the Fuji temp kit, and it basically is a close shot here. We take an RTD, we use a thermal compound, looks like a zinc oxide, apply that to the pipe, and we strap it on with a flex tape and leave it there. You can re-insulate after it, not going anyplace. So a precision RTD, much more accurate than the stated accuracies there. It's considerably more accurate than the stated accuracies there, and calibrated to work with the system. It's plug and play. The GE PT878 also has similar RTDs. They're strapped on the outside of the pipe, and they come through their IO port right here through a Y connector. Now, the installation of RTDs for temperature, again, I said it's about accuracy. We bought really intelligent flow meter and a really accurate RTD, and guess what? We put it on the pipe wrong. If we put one on the top, we put one on the bottom, we could have a couple degree temperature because hot air rises just in the basic installation. So when doing differential temperature monitoring, you have to do similar temperature sensor installations, not on both at 3 o'clock or 9 o'clock. In that case there, we won't have the differential just through installation there. Everything you can do to enhance the accuracy that you need to do. So in monitoring BTU, it's a lot of data. We need to monitor flow. We need to monitor supply temperature. We need to monitor return temperature. We want to look at BTUs or variations of BTUs. And in that case there are multiple data points. So there's a gotcha where you need to monitor the meter or that you're going to have is a lot of the meters out there only have 100,000 or 150,000 data points. When you do a flow study for energy management, it's not a quick trip. Most people tend to leave it there for a week, a month, or more in some cases there. So you need lots of data. So the only meter out there that has a large data storage is the Fuji, which has a couple gig SD card, and you can store data until the cows come home. Remember, each data point, each item is a data point. So if you just were logging one data point like flow, once a minute, it's 1,440 data points in a day. Then you want to add temperature times 2. You want to add the other temperature times 3. You want to add the BTU and other outputs for BTU. You could have a half a dozen points times per minute. So you can see you can eat up data very quickly in energy management applications. Some energy studies take an extended period of time. Sometimes when we go to a university, they would say, we would like to look at the energy over the summer. So we would like to rent 14 meters for 3 months. And sometimes the economics aren't practical. With that in mind, in many cases there, we know that these are going to be primary metering points, so why not make the investment and buy 14 dedicated energy meters for probably the same price you're going to rent 14 meters for 3 months. In this case there, we have a dedicated device, and it would read the same thing as the other flow meters there, strap on temperature on the supply, strap on RTD for the supply, strap on RTD for the return. And the key here is tie it in to the university or the building's own building diagnostic system. And that's where the things have evolved is the communication. So we can use their own building automation systems to log and compile the data. So in this case there, if they have something that takes 4 to 20 or Modbus or Ethernet, and some of the newer facilities will have BACnet, MSTP or BACnet IP, Modbus or TCP/IP, so you plug in an Ethernet cable, basically, Ethernet jack, that's just plug and play and talk to the systems to dump the data on the building automation system. So there's really no reason from an economic standpoint to either rent or buy equipment to conduct your flow study. And guess what? After your flow study, now you have sub-metering for your primary controls. How about that? Flow study and a capital improvement all at the same time. And then it comes another form of communication too. I don't want to run Cat5 cable all over the place. I've got some disconnects, some buildings. I need to use a wireless system. It's all a matter of money, but yes, you can actually fire up most meters now, add a wireless system there to transmit to a central data acquisition system there. So there's no more excuse for transmitting data or compiling data for your energy management system. So first off, we need to know that we have to monitor energy for multiple reasons. One, we need to have this facility optimal and efficient, the best way we can run it for monetary reasons, and also resources are becoming scarce. So if you'd like to continue having resources, we have to recycle what we have, and we have to be as efficient as we possibly can with our energy and water applications. So once we get inside a facility, step one, we have to go through a discovery process to establish a baseline. What do we have? Well, someone's going to come here and sell us a brand new chiller system. It's going to cost us, millions of dollars there, but you're going to get a return on investment in the next 5 years. Okay, how bad are we? We don't know. Go and get a discovery process. Go monitor all the sub-metering to have a baseline. Go then buy your brand new chiller system and come in, and after that's installed and fired up, come back and do a second survey to see if there's a differential from the previous to after the customization. Sometimes it's not there. Don't make assumptions. The access to buy or rent technology to resolve your situation is inexpensively and easy to do. You can make guesses on energies for multiple facilities there. Here's one set of dorms, so they're all the same like that. They're not. Everything's always different. There's always uniquenesses in the application that you can't see, and it's so inexpensive to monitor these applications now. Break it down, do it as wide of a span that you can. As far as best practices, I mentioned there's a couple different features to look for in metering devices. You got to look at flow rate, rangeability, how low can this flow meter go. You have to look at temperature, logging information. Data logging storage is an issue. So pick the device that has the largest logger so you can compile your data, and also easy to work with. Some of the ones with the SD card don't even require software. You just turn it in, plop in your computer, and use Excel. Software and cables have been my nightmare nemesis for years using loggers there. So monitor the features that you need, and overall look at the economics. Portability is great, something easy and light to carry around. You no longer have to carry around those big old suitcases you used to carry around years ago. Everything's getting smaller, more manageable, and easy to use. As I said, accessibility, you can get anything online you want now. About us, we've been around for a very long time, over 37 years, and basically we're a group of engineers that specialize in ultrasonic flow meters there. So we provide technology as far as rental and dedicated meters for flow and for energy management applications. So information that you might like, it's available on our educational website there. If you'd like to get product data and any of the things we talked about today, you'll find it there, operation manual or data sheet. Also, we'd like to record as many webinars as we can. We're going through an expansion right now in our gallery, so not everything is up there, but the product data is up in the individual products, so feel free to watch additional videos there, again, at your convenience there. And of course, if you need any supplies, cables and grease, and anything you're busted while out making your flow survey. So, as usual, I always talk too long. We appreciate your attending our program today. Stay tuned for our emails. We try to have a webinar once a month. So, of course, there'll be another one up in August coming up. If you do have any additional questions, we will leave the chat function open for a couple more minutes, and I will conclude the audio portion of our program. Again, this has been Brent Baird for InstrumentsDirect. Thank you for attending our webinar session today.